The conditions for inference are slightly different when we're dealing with quantitative data, but the spirit is the same. So first of all, we need a random sample. So this hasn't changed at all. If we want to be able to generalize to the population, we need a random sample. So this is because we want to generalize to the population. If we don't have a random sample, or at least a representative sample, then all the calculations that we can do for margin of error and hypothesis tests, none of that's going to matter if we don't have a good representative sample as a starting point. The second condition is also the same as previous units. We want to make sure that our sample size is large enough. But the way that we check this is going to be a little bit different. So let's go back to that applet that we used before, tinyurl.com/3000-1mean. But instead of taking the first sleep population, let's look at sleep 2. So you notice that this population is skewed right. How is that going to affect our sampling distribution? So let's start off just with the default here, taking a sample of size 10. So the dots here are showing the 10 people that were randomly selected. You can see their sleep times in the second graph. 8.05 is the sample mean, and that's getting plotted in the third graph. And just like always, the samples are going to turn out slightly different from each other. We don't expect to get the sample mean each time. And we're starting to build up a distribution of sample means, which is called the sampling distribution. Let's do a whole bunch more. So notice that sampling distribution is slightly skewed to the right, not as bad as the population, but just a little bit skewed to the right. And so if we tried to use a bell-shaped distribution for calculating p-values and critical values and stuff like that, that wouldn't be valid. It wouldn't be valid because the bell-shaped distribution isn't a good fit. But what if we change the sample size to something larger, let's say a sample size of 30? Now the sampling distribution is looking pretty good, and it would be reasonable to use a bell-shaped curve as a model. So the truth is that the larger the sample size, the better the bell-shaped curve is going to fit, but a lot of times we need just like a rule of thumb cutoff, and so for that we're going to say that our sample size needs to be at least 30. But what if our population hadn't been skewed like this? What if it had been fairly symmetric from the beginning? So I'm going to go back to sleep 1, and you can see this distribution is a lot more symmetrical to start with. And I'm going to go back to the small sample size. I'm going to take a sample of size 10 from that population. And you can see that the sampling distribution is already nice and bell-shaped, even with a sample size of 10. So another way that we can check the conditions here is to check the shape of the distribution. So either you can have a large sample size, or you can check to see that the quantitative variable has a bell-shaped distribution to begin with. So we were showing it before sampling from the population. Usually you don't have a graph of the population because you're not going to have the whole population available to you. So instead what we're going to check is the graph of the sample. And if the graph of the sample looks pretty nice and bell-shaped, then you don't have to worry so much about the sample size.